Hi, my name is Owen Barthelmes. I am the Director of Engineering for the RF division of Amphenol. I'm part of the Amphenol Broadband Solutions Group, and my focus is interconnect technologies that complement the suite of products that Broadband Solutions offers. Today I'm going to be focused on introducing a new product that we're very excited about. This new product is called the NDX connector, and it is designed and intended for this broadband market. So the genesis of NDX, where did NDX come from? Well, it all started with an evolution first of the CATV systems themselves. As you look over the years, the CATV systems have evolved, starting with DOCSIS 1.0. Of course, there were systems even before that, but DOCSIS 1.0, 1.1, 2.0, 3.0, 3.1, which is what we see as most of the deployments out there right now. And then, of course, we have DOCSIS 4.0, which is forthcoming. Through all these years, we've seen a lot of evolution in the connector systems that have been used in these various systems. But we haven't seen a lot of evolution in the connector that's used specifically for RF in this market. So, it's going all the way back to the 1950s. We see there's a Type F connector that was introduced. Composite video was introduced. And there's been a lot of improvements to many of the interconnect solutions over the years. A composite going to S-video, going to component video, to HDMI. We have various other interfaces that have evolved, but we haven't seen any evolution of the RF connector itself, the Type F connector. Amphenol itself has a lot of history with high performance push-on connectors. And so as we came to this new challenge of how can we design the best connector for the broadband market, broadband networks, we looked at what we know already, what works well, what we've used in the past, and we built on that with some new technologies. We've seen now that Type F has kind of reached this useful limit with DOCSIS 4.0 being introduced. As 4.0 is introduced and we're pushing frequencies from the current, in general, 1 gigahertz type systems that are out there in the networks. Now we're pushing to 1.2. We're seeing a new push all the way to 1.8. And the DOCSIS 4.0 spec is being written around a 3 gigahertz maximum, which is a pretty significant jump from the 1 gigahertz systems, which work well with Type F connectors today. So we see this as a new challenge moving into the future. We were inspired as we developed this new connector by best practices, not only from connectors that we produce ourselves, but across all of Amphenol and all the technologies that we bring to multiple markets, and looking at what were the best performance, ergonomics, and ability to adapt to high volume in the future as these new high performance systems are deployed. So with NDX, we're combining some new patent-pending features that satisfy tomorrow's requirements, that layer on top of the best practices that we know for interconnect across multiple markets. So NDX, what does that stand for? NDX stands for Next Generation Dual Shield Extended Spectrum. So that's really the key of the interface. And what we did is we deployed this product is we really set a mission statement to look at 5 key areas, as you see here in the presentation. One key initiative was to provide an intuitive user experience suitable for consumer level usage. This is really a key for the interface and a key building block. We know that this connector gets deployed out there in the field and consumers use this very much like they use an HDMI connector, an Ethernet connector. These are connectors that they've come accustomed to and consumers use on a daily basis and they're familiar with. So we wanted to have a similar user experience than those types of interconnect. We also wanted to enable bandwidth expansion, not only for this next generation of DOCSIS 4.0 that's being released, but also for future systems, future protocols. So we wanted to develop a lot more headroom into the interface as we launch this. We want to deliver compatibility with the existing tooling infrastructure. So look, we know there's a lot of tools out there. There's a lot of technicians that know the current product well. They have all the tooling needed to put this, to build the networks and keep them running well. We wanted to really be compatible with that and not change that too much. We wanted to reduce the total cost of ownership across the value chain, especially reduce truck rolls. The current climate, more than ever, self-installs are critical, and we need a product where this can be sent to any customer. They can pick it up, and it's very intuitive. They can install this themselves, and it doesn't introduce any new issues that may have to be diagnosed by a technician in the field. And ultimately, we also need to achieve high RF ingress protection against current and future wireless bands. As we know, in the current systems today, there's a lot of potential interference between LTE and the broadband networks. But as we expand into new bands, as we expand up into the 1 gigahertz, 2 gigahertz, 3 gigahertz bands, we come across a lot of other potential interference that we need to protect against. So high RF ingress protection was also a critical component. So let's get into what this interface is a little bit. So as we see pictured here, this is a typical configuration for this interface. We see what we call the plug side here, attaches most commonly to cable. And then we see the jack side, which would be most likely installed inside of premises equipment, say a set-top box or a cable modem. And really key feature of this interface is it's a push-on, snap-on interface. It's not a threaded interface. The plug itself is a fairly simple construction. It's got a pinned interface, and then the jack is a little bit more complex in terms of components and design, and really some key features that enable its high performance. But we really focused on best practices, as I said earlier, in manufacturability, so that we could scale the manufacturing of this to very high volumes as this starts to be deployed into DOCSIS 4.0 systems. So we used heat metal stamping and forming, injection molding, automated assembly, processes we know well from other industries and know that adapt well to very, very high volume production at a very attractive price point. This is how the product looks. As you see on the cable side, really straightforward, quite simple design. We really attempted to keep it that way. As you see, one key feature is the compression crimp. So that essentially this back end of the connector that attaches to cable is identical to all the Type Fs that are out there today. Can be adapted to any compression crimp style design that exists today. And then all we've changed is the front side of it, which is the new NDX interface. As you can see here, it's a pinned interface. It's a round machined interface, quite a simple construction, not a lot of complexity, but a lot of key features that enable the technology. Then on the jack side inside the equipment, we have pictured a right angle connector down to a printed circuit board. It can be a vertical connector, can be edge launch, can be all the different normal configurations we're used to in RF type products. But this is a sort of a standard configuration that we envision being high volume. So you can see it's very similar to, say, like an HDMI or a USB type construction with the manufacturing method, which really enables this to be a low-cost, high-performance product that can be scaled to high volume. This is how the product looks integrated into a cable modem. And really, this is really the key to the product is when you take this product and you use it and you actually just engage the connector, it's a very simple thing, but it has a very user-friendly, audible, tactile feedback when you engage the connector and mate it. So you hear it, you feel it, you know that it's fully mated. It's not a high force to mate it, it's just right. You click it in place, it feels solid. You can hang the modem by the connector and it does not come apart. You can shake the modem, it does not come apart. It's a very solid connection, but also if you demate it, you just need to give it a little bit more of a pull, disengages. Very simple to use. We think that the consumer will really embrace this new technology. It can also be adapted to conventional wall plate home installations, should that be a need in the future. On the outside of the wall plate, of course, would be an NDX connector. On the inside of the wall plate is could be a Type F connector, or it could be NDX. So it could adapt to existing infrastructure, or it could be a complete ground up home wiring or commercial wiring application where NDX is used throughout the entire network. It really is flexible in that way. So let's talk a little bit about what makes the interface special, what is different about this product. As I said before, we named this product a dual shield product, and that's very important. If you look at the interface here, we actually have what we call a primary RF ground and a secondary RF ground. The signal line itself is shown here in the center, pretty straightforward, pin and socket joint. As I said, the interface itself is pinned, which makes it very robust, allows us to put low conductivity or high conductivity, low contact resistance plating on there for long product life, and have very consistent length and diameter versus a connector that may use the cable as the interface. But as we move to the ground is really the key of the new technology. You see that we first had this primary ground, and this is a spring contact system, and the ground makes contact to the jack, makes contact to the inside of the plug, and it's a very robust electrical connection. So this is the primary electrical connection point. It's located very close to the interface itself, which enables it to be a high frequency connector. But then as we move outward, you see there's a secondary RF ground, and that is really the key to the interface. This secondary ground embraces some technology that we developed in other products or have seen in other products, where what we're able to do is mute any RF ingress by strategically placing a ground in the right location. So in this product here, what we've configured is a ground right on the outside of this mating connector, and through a lot of analysis and testing, we found that that actually creates really great RF ingress protection by creating the second contact joint here. We also use this second contact joint as the mechanical joint itself. So you can see there's a detent in the outside of this plug connector. As the plug connector gets pushed in, it flexes out this flexible contact member and then snaps into place. That's what gives the audible tactile feedback of the mating system, but at the same time we're using that as an electrical contact joint. Now, one kind of secret of the interface is we put this mechanical joint on the outside of the connector versus on the inside of the connector like it is on some other connectors. That's really critical for this because this mechanical contact joint is a lot more aggressive from a mechanical perspective. It wears the plating more, it wears the metal more. We want to keep that away from the primary electrical joint. So we have a nice smooth contact joint for the electrical primary ground. That ensures that we have consistent performance over very high mating cycles. But then we move the mechanical electrical joint to the outside, so as this starts to wear over high mating cycles, we don't introduce any issues to the interface itself. We keep them on the outside of the connector. So it's really just a basic key feature that enables this technology in the NDX. Also from the interface itself, it's completely closed entry. You see we have some protruding dielectric on the inside of the interface. This is key. This protects these outer contact ground shield fingers, spring fingers, from ever being damaged, so it makes it much more robust. It's also a closed entry interface, so the pin is guided into the female socket, so it makes it much more robust and positive mating. And the interface itself is also scoop proof, meaning as you mate this connector with the plug, if you come in at a very high off angle, very aggressive, doesn't matter how you try to mate this from the side, the interface is recessed in this jack body, and what that does is it forces the plug to be fully aligned before the connector mates. So a lot of subtle features we've integrated together to make this a very robust product.